All right, so let's look at 2.7 number 16. What do you guys come up with here? So they're telling me I've got two symmetric matrices A and B, and they're asking which of these things are definitely symmetric. What do you got?
I only got as far as part A.
Okay, so to look at part A, what should we be doing?
So, what I did was I went back to that one thing that we proved earlier, which is AB transpose is equal to B transpose times A transpose.
Okay.
And so if instead of AB in there, we have A squared or A times A, right?
Okay.
And then that gives us A transpose times A transpose. So, and since A transpose is equal to A, then we know that A squared is symmetric, and then we know B squared is symmetric. And if you have a symmetric matrix and subtract a symmetric matrix, you're going to have a symmetric matrix.
Okay. Cool. Yeah, I'll buy that argument. So another way you could kind of run that is you could think, okay, so if I transpose this matrix, that's the same as doing A squared transpose minus B squared transpose. This maybe takes just a little bit of thinking, that if you subtract and then transpose, that's the same as transposing and then doing the subtraction. It takes just a little bit of thought, but I think you guys can fiddle through it. It's there. And then, yeah, A squared transpose is A transpose, right? So that's A times A transpose, which is, and I guess minus B times B transpose. So that's A transpose times A transpose. It's hard to tell, but those A's switched order there, right? And then I've got minus B transpose B transpose. Again, those B's switched order there. And then, yeah, this is A times A minus B times B. So that's A squared minus B squared. Okay. Yep. Check. A is definitely symmetric. B is probably a little harder. It feels like B is just a factored version of A, right?
Yeah.
Keep in mind that matrix multiplication is not commutative. So this is not necessarily the same as this factored version. You'd need to know that A and B commuted for that. If you were going to multiply this out, you can do that. You just have to be very careful. So if you wanted to multiply this out, you just have to think, okay, so I'm distributing A in here. Right, so I'm going to have A times A minus B plus B times A minus B. And then distributing in, I guess I did that the kind of other way. Sorry, my pen has decided to act differently today for some reason. This is good. You know, it's fun when you plug this thing in and you get random functionality out of the buttons.
That's not functionality.
So after we've kind of multiplied this thing against that, then we multiply in. So we got A squared minus AB plus BA minus B squared. You guys with me on that? And in order for this to cancel, right, in order for this to be the same as A squared minus B squared, I would need to know that A, B, and BA cancel here. And they don't necessarily, because they might not be the same matrix. You guys see that? Okay, so if I think about transposing this whole thing, right, I'd get a squared transpose minus ab transpose plus ba transpose plus b squared transpose. And the a and the b ones I already dealt with, right? Those are just a squared and b squared. Oops, and I don't know why that turned into a plus. So those I dealt with before, but these ones are the ones that are weird, right? So I'm going to get B transpose A transpose out of that first one. And then I'm going to get A transpose B transpose out of the second one. And I am frankly not that sure what to do with this thing. You guys see that? I'd need to know that that was equal to AB plus BA. And I guess I know what to do with the transposes on these because A and B are symmetric, right? So I guess I can say this is A squared minus BA plus AB minus B squared. But I still have this problem that here I have a minus AB and here I have a minus BA. And here I have BA and here I have AB. I don't think I know those are the same. Those feel like they're off by a minus sign from each other, right?
Right.
Okay, so if I could make up two symmetric matrices that didn't commute, then I would know that this doesn't have to be the case. So to counter example, I need A and B symmetric with AB is not BA. Do I know two matrices like that off the top of my head? A couple of symmetric matrices that don't commute. Totally honest, I don't have an example for that right away. Is with me? So I might go digging. We're kind of out of class time for the day, so I'm just going to do these other two quick. I'm going to say right now that part B is not certainly symmetric. It could be, but it would take a deeper thing. It would take me knowing that symmetric matrices A and B always commute, and that seems wild. I think they would have said that in the book if it was true, you know? So basically, skeptical. And I know how to go about finding a counterexample. Now, for these guys, I want to think C. I want ABA transpose. What's that? Remember, you have to switch the order, right? So if you have a bunch of matrices all transpose, you just take them backwards and transpose them all. So ABA spelled backwards is ABA, transposes on everything. Notice this matrix here is this one. Right, they're reversed order. In this case, it doesn't really matter, right? And then because they're symmetrical, I know that this is ABA. You guys with me? Okay, so I feel like I can get a check on that. How about this guy? If I take AB, AB, transpose the whole thing, what do I get?
B transposed, A transposed, B transposed, A transposed.
Good. B transpose, A transpose, B transpose, A transpose. Very nice. Just switch the order, throw a transpose on everything. Then notice that B transposes B, A transposes A, B transposes B, and A transposes A. Is this one the same as that one?
Oh,
This comes down to needing the same thing though, right? I still need two symmetric matrices that don't commute. So I feel again like I'm skeptical on that one. So in order to know for sure, I need to know, again, two symmetric matrices that don't commute. Okay, so your task is now to go ye forth and find me two symmetric matrices that don't commute. If you can do that, then you have the answer to 2.7 number 16. If you can't do that, then you owe me a proof that two symmetric matrices must always commute, which is probably not true. Cool. If you're going to guess and check to find two symmetric matrices that don't commute, try using the little Python calculator that we built. That way you can guess and check and do multiplication quickly and you don't have to, fart around with it. Cool? All right, I'm going to stop this.